Oh, there we go. All right. Thank you and welcome to United Astronomy Clubs of New Jersey. Once again, we're back on site. Second presentation of the season uh, here in Jenny Jump State Park. Normally, I'm the one dancing, which is why I'm like, yay, I'm not the only one. We're here in Jenny Jump State Forest in Hope, New Jersey. Thank you all for joining us here, both here in person and online, because we do live stream this to both YouTube and Twitch. Okay, so I'm going to go a little bit longer than normal because, first off, speaking of Twitch, big news. You guys pushed us over uh, the other day when we live streamed our solar eclipse Monday, April 8th, and now we are officially Twitch affiliates. So, in addition to hitting those free options for support, which are the like and subscribe buttons on YouTube and Twitch, you can also now sub to us as well. And that money does go to helping us do these free outreach programs and special events. In addition, you can check us out on our website, uacnj.org. It's where you're going to find a list of all our upcoming talks, a list of what the talks are, our presenters. It's also going to have a list of all our member clubs because we are a club made up of other clubs trying to reach as many people as possible with our love of astronomy and science. In addition, if you're ever wondering about events or have questions, you can reach out to us on our social media. We have Facebook, Instagram. We also have a Discord channel we'd love to see you in. All those links, you can find those on our website again. So, now that I see most of our guests here have actually wandered down, now is time for the safety briefing for those of you who have joined us here on this blustery, windy day. First off, if you need to use the restroom, that is the porta potty in back. To my left, your right, it is illuminated by red, so in the dark you can kind of almost see what you're doing. After the presentation, we also have a little museum area and gift shop. Feel free to look around. I'll be manning that after the presentation. So as it gets dark, because we are just coming off of a solar eclipse and therefore a new moon, it will get rather dark. If you have any flashlights, do keep those lights pointed towards the ground. We don't need to accidentally blind people. When we go to leave, also, because many of us came here in cars and didn't hike 20 miles from our house, we are using our headlights when we leave, even though, yes, that does affect our night vision. We don't enjoy getting run over, and I'm sure you also appreciate that sentiment, besides way too much paperwork. All right. So, also for you guys here, it looks like we do actually, after the presentation, have one observatory, at least one. There might be another. I don't know. I don't have my distance glasses on, which help me see farther. But yeah, each of those sheds with the roll-off roof does contain a telescope, and one of our volunteers will help you look through those scopes. With that, we're going to get into our presentation for tonight, which is Heliophysics of the Cosmic Shore, with exploring Earth space weather with Lindsay Goodwin. Lindsay Goodwin is a physicist specializing in plasma physics in the geospace environment and coupling from the sun to the Earth. Lindsay received their Bachelor of Science in Physics at the University of Calgary in 2005 and their Master of Science in 2014 and their PhD in 2018 in Physics and Engineering at the University of Saskatchewan, after they went on to fill a postdoctoral research positions at Boston University and the New Jersey Institute of Technology, before being awarded the Jack Eddy Fellowship, which is a NASA program, Living with a Star program, in 2020. Now they are an assistant professor at the New Jersey Institute of Technology. And here is Lindsay. Also, if you have any questions, we do have a question and answer session at the end where we'll walk around and get all those questions answered, okay?
The internet here. I'm a loud talker, so I'm going to try and whisper as much as possible. Am I? Yeah, you might have to move it real far away. Okay, I'm good. All right, cool. Uh, Hello, everyone. Welcome. I've never done a presentation this late at night, so I'm like, who all's out there? And I hope everybody's keeping warm and stuff like that. But yeah, thank you so much for coming out tonight. Supporting astronomy and fun stuff and amateur science and fun, awesome things. I have like a really fancy title. I said Heliophysics of the Cosmic Shore will be my talk. Have people heard of the term cosmic shore before? Someone quoted that. Carl Sagan would talk about the idea of like the cosmic ocean and going out, and now we're just stepping into the era of where now we're exploring the stars. And not just like looking at it through telescopes, but we're sending spacecraft out there, like the Voyager mission, for example, that goes to the edge of the heliosphere. I like to think in that context that what I do is I look at this thing called the cosmic shore, which is the space right close to the Earth. Another way of saying that is it's the interaction of the Earth with like the solar system and like how, and particularly the sun and what the sun does to the Earth, if that makes sense. I think like the best way that I can very quickly introduce what I do is talk about the aurora. Have people heard of the aurora? Yeah. How many people have seen the aurora? A few. Oh, that's awesome. Yes. One of the kids too. That's awesome. Okay, so you've had the chance to like go up north, I'm assuming? Oh. You saw it in New Jersey. Oh, yeah, somebody's pulled out their own telescope and like looked out really far. Just repeating back so people online can hear. That's super awesome. Yeah, aurora down at these latitudes are kind of rare, but aurora are always present. There's always somewhere in the world that there's an aurora. And I'm going to click this video cuz I think it's cool. And I think I have to click it over here though. It takes a second to think about itself. But yeah, so we have this thing called the aurora, or the northern lights, or the southern lights, or the aurora borealis, or the aurora australis, is what you call it in the southern hemisphere. So this is spacecraft observations. You have a spacecraft with a camera that's pointing down. You can see that there's all these lovely cities. But you also see that there's these cool green structures, and like I think that like a lot of people don't really appreciate how much this is like a fluid, and like how you can see that there's all these structures that are appearing and disappearing and all these turbulent things and stuff like that. There's also like these kind of striations and lines that are appearing there, which like as we'll come to find out are actually like a consequence of magnetism and magnetic fields that combine not just like our own magnetic field, but the magnetic field of like the interplanetary magnetic field, like the outside of Earth, what magnetic field we have there. I will say that like the stuff that I study, like I stick to Earth. One of the reasons why I stick to Earth is because we have a lot of data. But just because I study mostly Sun-Earth interactions and the aurora here doesn't mean that like that kind of science doesn't apply anywhere else. So we also have aurora that's in other places in the universe. Does anyone know what that planet is? Jupiter. Cool. I'm pretty sure everyone knew that, but everyone was just kind of Jupiter. Yeah, it's Jupiter. Cool. And Jupiter is really interesting, the aurora that they have, because in order to have aurora, you have to have charged particles, as we'll talk about in a second. And where Jupiter gets those charged particles can sometimes be from like the moon being crushed. Like they have a whole bunch of moons, and like they'll create plasma just through tides and like crushing of like moons and stuff. So that's Jupiter. And with a little bit more enthusiasm, what's that one over there? Saturn, yes, that's Saturn. You can tell it's got the rings there. But yeah, that also has aurora. So it's not just us. There's aurora on Saturn. There's aurora on Jupiter. Some people argue that there's aurora on Mars, even though Mars doesn't have a strong magnetic field. It has like crustal variations, and that's how it has a magnetic field. But aurora happen everywhere. So it's not just that like Sun-Earth science only applies at Sun-Earth, and it can apply everywhere. However, some people will ask, okay, well, why do we actually care about Sun-Earth interactions and stuff like that? Like, cool, you have aurora, but like, what else do you have? Like, As if I need to tell them what else. But here's what else. So some people might have heard of the Hydro-Quebec event that happened back in the 80s. I know the 80s was a while ago, but this is just a really good example of like why we should be afraid. No, why we should concern ourselves about space physics. So this top plot here, you don't really have to understand it in depth, but this very top plot here is a measure of X-ray flux. So here we have the GOES spacecraft, which is just kind of hanging out like near the Earth. And it's measuring X-rays that are coming from the sun. And as you can see, there was one day where bloop, there's a whole bunch of X-rays, and then nothing, nothing, nothing. And what's going on in this nothing, nothing is that there's all this like charged particles and magnetic field that are traveling in the solar wind towards the Earth. Then about 3 days go by, which is how long roughly that stuff from the solar wind takes to get here, and then ba-blam! So what we have over here in this ba-blam area is magnetic field perturbations that are measured through magnetometers. Oh no! For those online, the shed is scary. But anyways, so here we have magnetic field perturbations that are caused by like something that happened on the sun. Some people talk about the sun burping and stuff, and like all these magnetic magnetic fields and charged particles came and basically hit the Earth. They pummeled the Earth. And the consequence of that is that we had all these currents that happened in the atmosphere, all these currents that happened in the ground, and then that's how we like destroyed a whole bunch of transistors and transformers and our power infrastructure that on the East Coast. So this was called the Hydro-Quebec event, where we had a large solar flare that then did so much destruction that we had. We had like a power outage for days while people were trying to fix this thing. Other kind of interesting stuff. I will meekly mention I'm Canadian, and so and I've been living in the U.S. for a while, so I'm naturalizing. I'm becoming one of you. But in Canada, we'll do a lot of things related to radio wave propagation. Canada's big, and we often want to talk to people on the other side of the horizon, and we'll do that with things like ham radio and fun stuff like that. And so what we'll do is we'll use the atmosphere as a way of bouncing off signals. We'll use like nearby like particles that are in the upper atmosphere and within space physics to try and talk over the horizon. However, the problem is that if the space environment nearby us, in this area changes, that will change how we can communicate over the horizon. So these plots here are just showing different radio wave propagation paths. So each one of those like little lines there is a kind of like a way that we could like shoot out a radio wave to try and reach over the horizon. And depending on what is existing in that area, we have different ways that radio waves can propagate. Have people ever like played with like Pyrex glass? I know that's like a fun children's toy. But like like Pyrex glass or like glasses of water, and like you dip a pencil in there and you kind of see that things bend and reflect. It's kind of like the same thing, that like you're trying to send light rays off into the sky to then bounce them along, but depending on what is there, you can change that. So these are just some plots showing that like in this top plot here we have one kind of condition, in the second plot we have a different kind of condition basically. And we call these like different structures that can exist within this region irregularities, because why not? That's a good name. I like that name. This is another example of the same thing. So this is, before we get into like the data that's shown over here, a little bit of context. So here's a zoomed in picture of Greenland and northern Canada. So there's a place called Kanak, and there's a place called Alert. And sometimes they want to talk to each other, and they use radio waves to do that. The bearing angle from one to the other, it's also referred to as thole sometimes, Kanak. The bearing angle is 200 degrees. And so you send like some radio signal at 200 degrees. Ideally, you would start talking to Alert then. What this paper here over on the right showed was that people were looking for this signal that was coming from Alert, but sometimes instead of looking over there, oh, the signal's coming from over there. Oh, the signal came from over there. So what these different lines back and forth are showing are different places where that signal was coming back. So what was going on was a signal went off into the atmosphere, went off into space, bounced, and then bounced sideways, and then bounced sideways back, and then finally, just by sheer luck, ended up in Alert, where it was supposed to be, which is pretty cool, I think. The last thing I'll say to kind of motivate why we should care about space physics and the near-Earth space environment, do people know of SpaceX? Nice response. I'm not gonna repeat that for the cameras, just in case like I'm being filmed. But yeah. So there's companies like SpaceX who are very invested in like putting spacecraft up into the atmosphere. And way back in, well, not way back, but in February of 2022, they launched a whole bunch of spacecraft, and about 40 of them had to come back or came back down. That's a nice way to say they like burned up in the atmosphere, I guess, and stuff like that. And the reason why was because there was a solar flare that happened during that time, and the livelihood of the spacecraft just wasn't ideal for that time. Basically, long story short, there was a lot of friction. The atmosphere and like the near space environment just kind of puffed out, and there was too much friction for it to stay up there, so it came back down. So that's like another important thing. But like even more generally, like depending like SpaceX aside and your feelings about SpaceX, like this affects our ability to have like people in space. It affects our ability to have spacecraft in space. So like understanding that environment and like just what's going on is important for like the safety of like having people and space infrastructure in space. I really like to think that like there'll be a day and age very soon where we will have spacecraft that like are there and accessible to everyone. And like our ability to understand that environment like is wildly important to do that. And so I think not only like should we like study it, but I think like everyone should have an understanding of what's going on there, because I don't think we're far away from like everyone from being like, oh, I shouldn't go out in my spaceship today because there was a solar flare. It would be like I shouldn't go out driving today because it's raining really hard, sort of things like that. We should have that sort of awareness, and I think everyone should have that. So I mentioned a lot about like space physics. I should probably at this point explain what I'm actually talking about. So what is space physics? So when I'm talking about space physics, I'm more like precisely talking about these things called the ionosphere and magnetosphere. Have people heard of those terms? Ooh, okay, yay, lots of people did. So that's awesome. So yeah, I study something called the ionosphere. Casually in conversation, I will say I study from about 80 kilometers off the ground. If I'm talking about the ionosphere, I say to about 1,000 kilometers. So this is kind of like the closer part of the atmosphere. We have these different regions called the D region, the E region, and the F region. The difference between them is just different chemistry. The D region is so complicated that I didn't even put it on the slide over on this side. The E region will have a lot of N2 in it, and will create like things like N2 plus. There's also O2, which creates O2 plus and O, and then there's the F region that has a lot of O and O plus that's existing in it. You might be wondering what about ABC? So the kind of little bit of the history of here. So when people started bouncing radio waves off of the atmosphere, they're like, oh, what is this thing? And they probed it a little bit more, and they learned that there was electric fields associated with it, or at least they had this idea of electric fields. So they're like, okay, so we're gonna call that the E region. That's the place where electric fields exist. Oh, so the place after that will be the F region, and over time we'll probably find a D, C, B, A region, and then they didn't. So now we just have the D region, E region, F region, because there is no ABC. So historical reasons, but yeah. Another way that I can show that sort of plot from before, but a little bit more precisely, are these figures over here. So the figure on the right, I'll start with, is showing ionized gas. I'm going to talk a lot about plasma in this. Have people heard of plasma? Ooh, is someone bold enough, is someone brave enough to tell me about what plasma is? Yeah, what's a plasma? Yeah, fair enough. I don't know your name yet. What's your name? Yeah, people talk about solid liquid gas. Yeah. Yeah. You're pretty close. Yeah. So, like the idea of a plasma is that it's a type of gas. People do talk about it like a fourth state of matter. But it's a kind of like an ionized gas where electric fields will act over really long distances. One misconception about plasmas is that it's hot. In fact, a lot of plasmas aren't hot because the interstellar medium is a plasma and the interstellar medium is quite cold. But that is one way that you can make a plasma that people talk about, is that you heat it up. But it doesn't always have to be hot. It can be quite cold. But this plot over here, over on the right, is showing plasma density, so how much of plasma is existing at a given altitude as a function of altitude. So we see that we start to have a lot of plasma at around 80 kilometers, and then to the edge of the atmosphere, about 1,000 kilometers up, we'll start to have like a more and more decrease in plasma. But yeah, like I guess for the purposes of this talk, and my PhD supervisor would kill me for saying this, it's a weakly ionized gas. It's an ionized gas. It is more complicated than that, but it is an ionized gas, and it's very fundamental to the universe. Cool. Oh, and the plot over on the left, I just wanted to show there. So this is a thing called the thermosphere. The thermosphere is just the area where you have a whole bunch of neutral gas, and I'm just trying to indicate that, yeah, even though you have a lot of plasma that's existing in a certain region, you'll also have a lot of neutral gas, and it will be very hot in that area. So getting to about like 1600 Kelvin up to about like Kelvin up to 1,000 kilometers. There we go. I finally said it. But yeah, so we can have like a lot of hot neutral gas in this area as well. But that's not the only thing. So the sun comes in and it creates a lot of this plasma, not necessarily through heating, but through this idea of like photoionization is what we call it. When like it gives so much energy to that neutral gas that you then create a charged particle. But the sun does other cool stuff as well. So usually when we talk about a magnetic field of the Earth, most people want to think of like this nice dipole sort of magnet that's almost like bar magnet. Like people, that's a thing, right? Okay, cool. That's still a thing. I'm not that old. That's great. Back in my day, we thought, anyways. But yeah, that's not actually what it looks like. And the reason why it doesn't actually look like is because the sun is constantly belching out magnetic field. This is not a 2-scale picture. This picture on the left, it's just a nice picture. So don't take it too seriously. So here we have the sun that has all this like mass and charged particles that it just like burping out into the solar system, and that will hit the magnetic field of the Earth and start to bend and distort it. A more accurate picture of like what the magnetic field of the Earth looks like is this thing over here, which is way too complicated, so I'm not actually going to go into it. Instead, I'm going to go into this much simpler, much nicer thing. So we call this the magnetosphere. So I study the ionosphere, which is closer to the Earth, but there's also this idea of the magnetosphere, which extends like 30 Earth radii away. It's a really big boy. It's a big boy. So over here, what I'm trying to show is how the magnetic field of the solar wind interacts with the magnetic field of the Earth. So what we have over here, can I step in here? Okay. Yeah, I can be this close. Okay, cool. I don't know why I'm just like afraid the door is gonna close and I'll be trapped, and then that's it for me. So what we have over here is a magnetic field of the solar wind. The magnetic field isn't always pointing in this direction. It's just a diagram. Don't take it too seriously. So here we have magnetic field pointing southward. We say southward if it's pointing down like this. But ultimately, it will come and it will hit the magnetic field of the Earth and will start to merge with it in this thing that we call day-side merging, which is what this GIF over here is showing once it restarts again. So here we have the solar wind magnetic field and the magnetic field of the Earth. They'll come close together, and then they'll pinch, and then these field lines will go off in different directions. And that's what we're seeing here, is that bloop sort of thing where they drift off. However, just because the solar wind hit the Earth and now shares a magnetic field doesn't mean that the solar wind is going to stop. The sun is big. I think we can agree. I don't know why I said that like as if someone's going to be like, well, actually, it's not that big. But we have like so much inertia and so much momentum associated with the sun that the sun and the solar wind from it, rather, is going to drag those magnetic field lines from the Earth. It doesn't care that the Earth's a magnet. It's just a tiny thing compared to the solar wind. So we'll move from the magnetic field that we see from 2, but then the magnetic field will get dragged this way, which we call anti-sunward, or towards the night side. It'll get dragged, it'll get dragged, it'll get dragged, and then way far deep, like away from the Earth. And like that's why I say about 30 Earth radii is where I study. It's like really far out. Finally, the relationship between these two magnetic fields will be so tenuous that the magnetic field of the Earth will reconnect with itself. We call that reconnection, and will sort of like zip back towards the Earth. So we have this like huge, large scale, we call it convection, even though it's not technically convection, magnetic field lines moving, connecting with the solar wind, moving anti-sunward, and then zipping back. Or I could have just played this video right off the bat. This one here. So that is explaining more simply, basically what I said is that we have the magnetic field of the solar wind that then connects with the magnetic field of the Earth and starts dragging it around and stuff like that. That kind of makes sense? Yeah? Okay, cool. Oh, I appreciate the nods. Cool. I still can't quite see everyone, but I can see that, and that made me happy. So thank you. Just in case, I recognize them on Twitch, and so maybe there's some actually comments in there. So I'll just quickly address that. Like, this is an idealized model. It usually doesn't happen like that. There's usually what happens is there's a bunch of reconnection events, and this is just some data that's like associated with that, or mostly it's models. So here we have 4 spacecraft that we're measuring like the merging of the magnetic field with the merging, of the Earth with the solar wind. And it found that like there are inconsistencies with that. It's not just always a nice model, but there'll be like multiple reconnection events. So this over here is showing the velocity of plasma. This is showing what direction is the magnetic field in that plasma pointing. This is the density of plasma, and this is that BZ or B7? Weird. Okay, I thought it was BZ. Anyways, so it's not always so nice. You can have multiple reconnection sites and fun stuff like that. However, if I'm moving my magnetic field around, my charges are probably going to do something. I realize this is a talk for like the general public, and like I don't necessarily want to like go into the whole like, well, if you have charges that are moving in a magnetic field, they start gyrating around and bouncing and all this stuff. But can we kind of agree that like charges like to do stuff with magnetic fields? Yeah. Okay. Cool. Let's leave it at that. So. What will happen is the charged particles, the plasma that's associated with the Earth, will see those moving magnetic field lines and be like, oh, I want to do that too. I want to move around. That looks like fun. So this here is a picture. It's a top-down view of the Earth. So we're pretending that we're in our spacecraft. You're not really supposed to stand in front of presentations, but whatever. And like I am staring down at the Earth from the North Pole from here. That's the view of this picture. So this is the noon side of the Earth, or rather like the side that's like daylit. This is midnight, the side that is not daylit. Here we have dusk, and here we have dawn. So this area here would be where we had that merging of the solar wind with the magnetic field, where they're coming together. And we see that plasma, these dark black lines here, wants to move in the way that the magnetic field is like pulling them around. So we have like plasma that like is moving because the solar wind has that inertia to keep moving away from the sun. So we have this moving of plasma. Then someplace way, way off, you'll remember that model from before, I was talking about reconnection, where the relationship between the magnetic field of the Earth and the magnetic field of the solar wind is so weak that the Earth is like, forget this, I'm going to go back to Earth. That happens and maps down to here. So plasma will start to boomerang back towards the Earth, and what that looks like in the atmosphere is that we have plasma that zips back towards the day side, like that. So we get this kind of like, we call it a 2-cell convection pattern, where plasma moves anti-sunward, zips back towards the day. We don't, like, in my field, in my field within my field, I don't really talk about this other region, but whatever, I'll talk about it now, just in case people are interested. This is the co-rotation region. In other words, my Earth is, like, spinning around, and magnetic fields spin with it, so it spins too, because why not? That seems like fun. So, how many people know of cathode ray tubes? Yeah? Wow, more than I expected. Okay, cool. I was feeling like a dinosaur, so that's good. So kind of what I'm implying in all of this is that things that happen out in the magnetosphere and with that magnetic field change the properties of plasma closer to Earth. Basically, if I move things around with my giant magnet, plasma within the Earth like moves around as well. Or right, closer to Earth moves around. So the parallel that I like to make is that basically the atmosphere is like a TV, if that makes sense. So we have this thing called cathode ray tubes, or rather, we don't use them too much anymore, but whatever. So here, how a cathode ray tubes, and yes, I know this picture's super old, but it's really helpful for explaining, so I apologize that it looks really old. So here we have an electron beam that's being made within our cathode ray tube. It moves along, and then it gets modulated by something, and then it gets projected onto our TV. Like, remember the old cathode ray tube TVs? Hopefully the children can relate with this. I see them there. So it will create some sort of image on like the screen of a cathode ray tube, and that's the atmosphere. So I have like magnetic field lines, and sometimes there's charges moving along them. And if I have something that's like modulating here, there's like a question mark here. If I have some sort of modulation that's happening, way out, like near Earth, but still like not that near Earth, that will communicate something down to the Earth and move plasma around. So these things that are like can be 30 Earth radii away are still really important for moving things around. I also just want to add a bit of a correction. So I was talking about like this certain kind of like 2-cell convection pattern of plasma moving around. It can get a little bit twisted. That's what these plots are showing here. So this is a clock angle here, which is basically what is the direction of the interplanetary magnetic field. Is it pointing southward? Is it pointing northward? Is it pointing towards the dusk? Is it pointing towards the dawn? The solar wind is a very complicated thing. It's not just always going to point in one direction. It twists and stuff. If you get really interested in solar wind, I would recommend looking up terms like the ballerina skirt. Like there's like this cool idea of like a skirt that's flying out from the sun, that like depending on what angle you look at that skirt, you'll see different magnetic fields. But I digress. You can see all these different like ways that plasma moves around. Up to this point, I haven't really showed a lot of data. So let's actually throw some of that in there. Why not? It's a science presentation. Let's talk about actual data. So here we have, and also maybe I'm standing in front of the camera. So here we have plots. Once again, we're sitting in our spacecraft. We're looking down on the northern hemisphere over on the pole. All you really need to know about these plots is red means lots of plasma. Blue, less plasma. These lines in here are kind of like guides along which plasma wants to move. And that's because the magnetic field is moving around. The day side of the Earth will have a lot of plasma due to photoionization. Plasma is generally made when there's a lot of photoionization, and just conveniently, the day side has a lot of sun. Somehow, I don't know. Anyways, funny how that works. So this side of the Earth will have a lot of plasma. But we can see that over time, because of like this 30 Earth radii, like convection and moving of magnetic field lines, that plasma will get swept up in this. And so from here, we have a whole bunch of plasma sitting here. But we see that over time, this plasma starts to get carried over onto the night side of the Earth. There's really dense plasma. And then it will start convecting back towards the day side. I emphasize this again. I want to like kind of like go back to like when I was talking about radio wave propagation and stuff, and how like that will change depending on what we see in the sky. That is very much related to that. So let's say I'm in Canada. Where's Canada? Oh no, I'm in Russia. Let's say I'm in Russia, and I'm trying to like send a signal somewhere. And I'm trying to like, I don't know, maybe talk to my friend in Iceland. I don't know anyone in Iceland, but let's say I do. And then like a whole bunch of plasma like comes into the way, and like that changes the way of like that my radio waves want to travel. I can't talk to my friend in Iceland anymore, and that's okay, like sad, like if I'm just trying to have like a casual conversation. But let's say like I am stuck in the middle of nowhere and I desperately need help. That becomes a problem. And like we find these situations in Canada where you have like search and rescue missions where like you need to talk to someone and you can't because there's a bunch of plasma that's stopping, or rather that's changing the way that your radio waves communicate. I also just want to throw in that like these GPS systems, like this changes GPS systems, by the way. It also affects farming, because a lot of modern farming is done without like having actual farmers sitting within machinery. So I guess like kind of like funnier stories that can happen is you have a bunch of plasma that moves into the way, they lose like that communication, and then you're like your tractor will start like off into the side just because there's like a mindless robot. So that's kind of more funny to think than like I'm lost in the middle of nowhere. So think about like tractors going off the road and fun stuff like that. I don't know. I haven't actually talked about the aurora in detail, and I figured that this might be a good time to do so. Because right now I'm talking about like magnetic field lines moving plasma that's closer to the Earth. So how does this create an aurora? This, I think, was the simplest plot that I could find that could kind of show that. So I talked about magnetic field lines that are booming, are like coming back towards the Earth, and this is kind of like a snapshot in time of that, where the magnetic field line has reconnected on the night side and is starting to come back towards the Earth, and we'll kind of like freeze frame there. So along those magnetic field lines, we have charges that want to move around. Charges love moving parallel to magnetic field lines, and they'll do like this sort of gyro motion, is what we call it. Basically, if you have a charge that's moving with some velocity in a magnetic field, it wants to spin in a circle. I won't make it more complicated than that. It spins. Just trust me. Ask me more later if you have any questions about it. But so it'll start spinning around like this. But the problem is that as this magnetic field line starts coming towards the Earth, it'll start accelerating that. And then what happens is ultimately those charged particles will fall into the upper atmosphere. Where, yes, we do have a whole bunch of plasma that's already sitting there, but those charged particles will want to interact with a neutral. They'll collide with a neutral and create photoionization. A couple of things to note, depending on where we are in the upper atmosphere, where we're looking, we'll see different kinds of aurora. So once again, this is top-down view of the Earth. Have people seen different kinds of aurora? What kind of aurora did you see, young man who's sitting over there? You don't know. That's fair. Did it look like discrete? Was it like nice lines, or did it kind of look like a cloud? Like a cloud? We often call those cloud ones diffuse, where it's kind of like you kind of look over the horizon, you're like, yeah, that's a yeah. No, that's a cloud. No, that's an aurora. Yeah, where like sometimes it'll be really faint. So we have diffuse aurora. We'll call them diffuse auroral patches sometimes. Where we have like all this kind of like diffuse aurora. There's discrete aurora, and those were those nice lines that I showed in that video before that those spacecraft were seeing as they were flying along. Just depending on like what kind of physics we're looking at changes what kind of aurora we're seeing. Also here, like I guess there's more diffuse aurora over there. So if you saw diffuse aurora, you might have been over there, you might have been over there. You probably weren't over here. So just to explain this plot a little bit more, this is midnight, 0. This is like army time, I guess is what we call it. If you're at 0, that means you're at midnight. If you're at 18, that means you're in the evening, so 6 p.m. If you're at 12, you're at noon. If you're at 6, you're at 6 a.m. Cool. And also, yeah, like as I kind of mentioned before, why the royal we all of a sudden? As I mentioned before, depending on like what your sun is sending towards the Earth will change the properties of the environment near the Earth, and we see that with the aurora. So this is an example of something that we call a substorm or a storm. Have people heard of geomagnetic storms and stuff like that? Yeah. So if I change the properties nearby the Earth, if I like do funky kind of reconnection and dayside merging and stuff like that, I'm going to change what my aurora looks like. If I put a whole bunch of energy into the near Earth environment, that's going to affect us. And that's kind of what is shown in these plots here. So they didn't put the timestamp, but basically you read it like this direction across. And we can see that as there's more geomagnetic activity, as there's more energy that's being deposited into the upper atmosphere, into the space environment, we start to see that the aurora gets all kind of funky. It not only goes to lower latitudes, but just the band of aurora that we see will become thicker and thicker and thicker. I also didn't really mention before, but I'll mention right now that we talk about this idea of an auroral oval, like because you can see that there's not a lot of aurora that are sitting in the middle. And that's because only when those magnetic field lines on the night side of the Earth have reconnected, that's usually when you have that acceleration of like charged particles coming down and raining into the upper atmosphere. Now quick quiz, why are aurora different colors? Chemicals. Ooh, it is chemicals. Yay, you got it. So we have 3 different kinds of aurora colors typically. So we have red, we have green, and we have purple. You don't really have to pay attention to this plot. This is me just trying to show that, yeah, there's a lot of complicated chemistry going on in the upper atmosphere. So we'll have purple aurora if like our charged particles collide with collide and create N2+. We will have green if we're looking at oxygen, and we'll have red if we're looking at oxygen. Wait a minute, we have 2 oxygens. What does that mean? So basically, depending on how energetic the particles are that are raining down into the upper atmosphere, that will change what kind of like ionization you can do to oxygen or oxygen. So we typically talk about the idea that like green aurora are closer to the Earth and red aurora are farther away, just because they're less energetic. Like they weren't able to get into the atmosphere as far. Cool. I felt obligated to talk a little bit about my own research, and so I'm going to do that. I feel that I worry that, like, I don't know, I'm self-conscious about my research a little bit. So I'll talk about it a little bit, and if you want to hear about it more later, that we can. But like, I don't know. I hope people want to hear about my research, so I'm going to talk a little bit about it. So how can we measure plasma? There's lots of ways that we can measure plasma. We can look at spacecraft. We can use cool optical instruments. We can first stuff about plasma. Over there was a shed that had its own Fabry-Perot interferometer, which is some fancy instrument that looks at neutrals. But from neutrals, we can infer things about plasma, which are really interesting. How I like to study plasma, I mentioned radio waves a bunch. It's radio waves. I like using radio waves. So I use these cool things called advanced modular inquiry and scatter radars, and I know that that's a very dry name. I also acknowledge that this doesn't really look like a radar. This is actually a giant panel that has a whole bunch of antennae that are sitting on it. So back when we started getting more into like space physics and stuff like that, but we understood enough about radio waves, we created radars that were these giant dishes that were like, okay, I'm going to point over here and I'm going to take some measurements. I'm now going to point over here and I'm going to take some measurements. And they were cool. All radars are cool. All radars are beautiful. The problem, though, with those instruments was that I could only look in one direction at a time. So if you have a steerable dish radar, I feel like I got louder, and it might have been because I hit my face. I don't know. Let people in the audience let me know if I'm really obnoxious sounding all of a sudden. I'm good? All right, cool. Okay, sweet. Thank you. So we create these new kind of like, I keep thinking there's a projector. We created these new kind of radars, which are all these antennae that are sitting on a giant panel. And the idea is that you create radiation patterns that are able to look in multiple directions for you. So this here is an example of like different look directions that we have from this instrument. You can run different kinds of experiments on it, but this is it. This is one example. This is the imaging LP mode. Don't worry, I'm not expecting you to remember that. There's not going to be a quiz at the end, or maybe there will be. I don't know. Maybe you should listen. But anyways, so here we have geographic latitude. Here we have geographic longitude, and each one of these points represents a place in space that's being measured. The color scale, which I'll try and shrink up for, is altitude. And what we can see is that we're able to look in multiple directions, like almost simultaneously. So this is a huge advancement over typically what we think about with radars and fun stuff, where we have like a dish that looks this way and a dish that looks that way. Because now we have like a panel that looks in multiple directions. It doesn't look as cool, but the idea behind it's cool. We have 3 in the high latitude. I study a lot of high latitude, probably because I'm Canadian and I'm a little bit biased. But also there's a lot of cool stuff that's going on there. We have the Poker Flat Inquiry and Scatter Radar, also known as Pfizer. We have the Resolute Bay Inquiry and Scatter Radar North. And if you have North, you have to have Canada. So this is the Resolute Bay Inquiry and Scatter Radar Canada. You can kind of guess who owns which. So this one is owned by Americans. This one's owned by Canada. And they're like, yeah, we got a fancy thing. We're going to call it Riser C. But it's really irritating because you want it to be Riser S. But anyways, so I use these kind of instruments to look at the atmosphere. So, let's not go back in time. There we go. So these are some observations that were taken with these instruments. So we have Riser C data from the top and Riser N data at the bottom. This is looking at plasma density, which once again is like how much plasma do I have existing at a given time. And we see that over on this side of the plot, we have a lot of nice dense plasma, and here we see a lot of weak plasma. So keeping in mind that I mentioned before that plasma can be made with photoionization, why do you think this plasma is more dense? So photo is like light, right? So when do we have a lot of light? On the day! Yeah, so this is the daytime. This is when you see a lot of plasma. And then over here, this is the nighttime. Yeah, and these dashed lines here show local noon and local midnight. But what's kind of curious and is that we see that over here, it's pretty dense plasma. Here we see, it's pretty weak plasma. But that doesn't mean that there aren't little pieces of still kind of dense plasma that are existing over here. And we know that like the magnetosphere is moving plasma around within the ionosphere, but we still don't completely understand why does a certain thing exist at a certain time. Put another way, and kind of giving a little bit more information about this. You might be thinking that maybe, oh, Dr. Goodwin, did you pick this because this is a really exciting day and this is like the coolest thing that you've seen ever? It's a cool thing. Yeah, it's on my list. But like this is actually a pretty boring time in the atmosphere. And in the space environment, like we typically like see like this kind of structuring, but from like the perspective of like what was the sun doing? Was there a solar flare? Was there a substorm? Was there a geomagnetic storm? Nah, not really. This is just what happens. But I don't have a good explanation for you as to what is this? Where'd that come from? Where's this? What's this? I don't know. But like that's a lot of what my research is about. So I'll show a little bit about what kind of events I've looked at. So there was that event, but I also like to, there's other events. I look at other times. I don't just analyze one piece of data forever. Otherwise, I'd run out of funding. So over here, this is a time when we had general boringness followed by something cool. So a crash course in like different geomagnetic parameters. This here is the AL and the AU index. The AL is in red, the AU is in black. Those are measures of currents that we have in the upper atmosphere. So what we see is like not a lot, and oh my goodness, there's like a substorm that happened here, and we can see that indicated up here. BX, BY, BZ, those are different directions of the interplanetary magnetic field. And we see that during this time they're not varying a lot. Sometimes they can vary a lot. You get all this like juicy like flux tubes and magnetic, or not flux tube, but like changes in magnetic field that will come at the Earth. And you can see all sorts of cool stuff here. This is not a good example of that. This is kind of like a boring time with the interplanetary magnetic field. And this is a different perspective on like those plasma density plots. So here, the colors here indicate plasma density again. And this is sort of a long track density. This is like taking a cut through my my plasma to actually see what kind of structures are existing. And we see that like during this time, like before this big quiet period, there was like structures that were existing. But then there was really not a lot that was going on. Then a substorm happened, and then all of the structuring started to appear. But what's kind of interesting, or what I've done, is that I've created like tools to try and look at more precisely what is going on in these quiet periods. And so these are some like quick findings that like I present to people, like you, people, humans, true humans. Anyways, so here we have plasma density at a long along like what am I trying to say? Like along like a cut that's through here. These different colors coordinate the different colors that are through here. So this black line is like looking at like this enhanced plasma. Here we have two lines that are looking when we have like nothing really going on, and then this yellow line is when after the substorm has started like looking at those structures. And we see that like it's very like when you actually start to look really close to these, you can see that it's actually very jaggedy and very like structured that we have. But we can do fancy techniques to try and look at like what scale sizes of structures are existing, and that's what this plot here is showing. I would call this a periodogram. I would also call this a Lomb-Scargill periodogram, which I think is kind of like lost on people. I would then try to explain that, oh no, it's just a Fourier transform, and then people are like, what are you talking about? Like, you sound crazy right now. So I guess the way that I'll describe it is that this is a plot showing basically how much of what kind of structures do we see at a given time. So over on this side, this is in a scale of frequency, which is kind of confusing. Basically, I'm saying stuff on this side of the plot is big, stuff on this side of the plot is small. So during the times of like blue, which is when we were in that quiet period, we saw that there was a lot of small scale structures that are existing. We saw that in this time, we would see that there are big scale structures that are existing. So basically what I'm trying to say is that we can find that like even in times when there isn't a lot of cool geomagnetic activity going on, we still see a lot of structuring that's going on. It's just not really big, and so we keep ignoring it because it's not as cool to look at. I don't know. Another plot that's showing this is a histogram. So this is a histogram, which is basically statistics. It's me saying how much of what kind of structures are existing at different times. MLT stands for magnetic local time, or if you want to think about it, it's like local time. What time is it right now, for example? Like 8:49. So 8:49, you would expect it to be night out, so it'll be like some sort of time that's like existing. What's 8? Yeah, 8, 9, 10. Yeah, so be around here basically is like 8:49 p.m. magnetic local time, whatever. And we can find by doing these kinds of plots that like in times when we get towards the night, we'll see lots of small structures. During the day, we'll see lots of big structures. Additionally, we can do other kind of cool studies like this, where this is associated with like geomagnetic activity that we're seeing. Crash course in geomagnetic parameters again. KP index just means is there a storm, is there not. The bigger that number is, the more storm, yes, there is. And so this plot is showing that in times when we have a weak geomagnetic activity, we see lots of small scale structures, but in times when we see more geomagnetic activity, we'll have larger structures that are existing. A final plot that I'll show before I wrap up is that depending on also the interplanetary magnetic field, that will change the size of structures that we see in the atmosphere as well. So here's the solar wind angle. So keep in mind, we talk about like the solar wind angle. I talked about it being southward hypothetically, but it can come at us at any angle. And that will also change the size of structuring that we have, particularly on the night side. Hello. So in like when the solar wind angle, depending on like if it's pointing like up or down or left, or sorry, not left or right, dawn or dusk, we'll see different angles. So it's when it's pointed more dawnwards, for example, we'll see more larger scale structures. But as it starts to point towards the dawn side, or sorry, did I say that backwards? Here, this would be the dawn side. Here's getting more towards the dusk side. We start to see more smaller scale structures, which is kind of weird. That it's weird that on one side of the Earth we'll see more smaller scale structures compared to the other side. I could talk more about that later, but I'll kind of leave that as maybe a question for the audience, or if nobody's interested in that, don't ask me about it at all. So I guess a quick summary, because people are getting cold and there's cool telescopes about, and I don't want to keep you for too long. I didn't really know how to summarize like a lot of like what the ionosphere, magnetosphere, and stuff, and I thought it would be boring to just kind of list every single thing that I've talked about with like the magnetic field and flares and aurora and stuff like that. So I just left the general space physics is cool. Yeah, it is. And like I feel like we want to talk about like astronomy, and like astronomy is great and stuff, but like we should also talk about it in the context of the Earth, and like how important is the sun to the Earth. When we start to get out to like other solar systems and stuff, like we need to understand that sort of sun, like that sun, and like the interactions and stuff. It's cool to want to understand the star in depth, but we can put it in the context of ourselves. And like, how are we going to interact with that thing? How does the sun affect us? Things like that. And that's what I like to study, is that it's not just astronomy. It's like, what is astronomy doing to us? What is astrophysics doing to us? And then I had to include a little bit of my own research, so I'll just quickly go through this. So, like, I found that, like, in my own research, that, like, there's different structures of scale sizes and plasma densities existing on the day side as opposed to the night side. You'll see these variations across, like, the Earth. And also depending on geomagnetic conditions you'll have like different sizes of structures. And again, put this in the context of either being lost in the woods and trying to have like a radio communication link. Maybe you're not able to do that because a whole bunch of plasma comes into the way. And so you'll want to know if like there's small scale plasma, if you want to know if it's big, or if you want to have a funnier picture in your mind, you can picture the tractor in Saskatchewan that doesn't actually have anyone in it, and then like it's having a hard time communicating and it doesn't know where it's going, and then it drifts off and then drives down the highway for a few kilometers. Like that's more funny. And then also depending on the solar wind angle, how the sun actually, like that angle of the magnetic field hits the Earth, that will change the kind of plasma that we see as well. And very last thing, thank you for listening.
All right. Thank you, Lindsay. So, first of all, you're always going to be more louder to yourself because our speaker's right above your head.
Oh,
It sounds normal to them.
Okay, good. Okay,
you just sound like you're screaming in your own head.
Perfect. That's what I normally do, so that's great.
Yeah, but I figured I'd let you know that you're cool.
Cool.
So we are going to have a question and answer session now. So I want to thank you all for joining us. Before we get into it, though, I'm going to go over to the safety briefing because usually a couple people sneak in during the presentation and did not get to hear that. So if you need to use the bathroom, porta potty in the back. It is illuminated by red. After presentation, I'll be manning the little museum gift shop area through the door to my left, and feel free to do that. It is also slightly warmer in there because, house. We also do have at least a couple of telescopes open that you will be able to look through, since it looks like a gorgeous clear night right now. So, flashlights, since it is kind of dark, if we're using them, we are keeping them pointed towards the ground because we don't need to accidentally blind people. However, we are using our headlights because we also don't like getting run over, and we don't want to see you run over because too much paperwork. Let's limit the number of paperwork and how many trees we're killing, since we're in a state park. With that, do listen to any of the volunteers' instructions. They will help you view through those telescopes. How the question and answer session is going to work is I have a microphone. For the people here, you're going to raise your hand and kind of wave it about like you just don't care. Mostly because I've been staring at a screen and I'm kind of night blind. So my vision is mostly based on motion right now. I am like the worst T-Rex. So, for our online people, you could just type since I have you on my wrist. So I'm going to start this off by the first online question, which is...
I'm so nervous because this is Twitch for some reason. Like, I don't know. I've never.
You don't have to be nervous.
Okay.
Was actually a comment that said, sounds like we need to raise money to get a less noisy / scary covering over the lecture area.
Oh yeah, that was pretty. Yeah, I was like, oh no, like, is everyone safe? Yeah, everyone's fine. Just so people online know, everyone's safe. Yeah, maybe a little cold.
It's fine. I personally tied and secured all the knots. So, and my father, who had taught me all the ropes and knots, would be very disappointed if it was not secure. So we are good. It is safe. So, hello. There it goes. Okay. I heard it click, and I'm like, oh no, did it lose audio? So, was there a question out here? And oh, perfect. Again, very bad T-Rex.
Hi.
Howdy.
So, you talked a lot about how radio waves and like that sort of communication can be messed up by plasma. Is there any way that, like, do people have a method to fix the communication if they know what the plasma is doing?
There are, like, it's kind of like the idea of, like, if we can forecast where something can be, we can work out a different, like, communication link, is the idea. You can't necessarily stop the plasma coming, because, like, that's just too big of, like, I don't know, it'd be trying to, like, move magnetic field lines of the Earth. Like, you can't do that. But you can, plan appropriately for that. Is like the idea. So maybe instead of like trying to have that connection from like connect to alert, maybe you could talk to somebody over there that could, or relay a message over there that could like mitigate that, if that makes sense. Similarly, if like you're trying to communicate with a spacecraft, and then suddenly you're not able to have that direct communication link, you can work out some arrangement with like maybe other buddies who have like ground stations to communicate with that spacecraft so that it always knows what it should be doing. But yeah, that's a great question. Thank you.
Right, so our next online question is, how can plasma be cold? Is it like how there are different boiling points for different types of matter, like different, aluminum and versus water?
That's really interesting. I like that comment. It's not so much that it's like made necessarily out of different materials. Like plasma can be made out of different materials. But it's just more so that like plasma can be made from like photoionization, right? And whether or not it like holds on to that heat is a completely different story. We have kind of like crazy ideas, maybe not crazy, but we have interesting ideas. I'll call that. That's a more appropriate term. For like what we like want to talk about, how we talk about temperature like in the atmosphere, and like that doesn't necessarily dictate like how a plasma is made. And in fact, like kind of getting into like a little bit more of the like the weeds and stuff, you can get interesting situations where like your plasma, depending on what angle you're looking at it, will have a different temperature, which is kind of cool. We call that temperature anisotropy. But yeah, it's not so much the boiling points though. That's like a really interesting thought. So I really appreciate that. But yeah, it's more so whether or not it holds energy. Oh, sorry.
It probably comes from, like when I was a kid, we were taught
Yeah.
it was the fourth state of matter and it came after gas. And when you boil water, it goes to gas. So if it's after gas, you must boil the gas harder. Not how that works. I don't know how you boil gas, so. All right. Was there another question out here? Perfect.
Hi, so this is a very, very specific question, and if
Okay.
nothing like this has ever come up, I totally get it. I'm biased in this question. I do research related to Titan. Is there any
Ooh.
difference in the way that magnetic fields affect something when it's not from the body itself? So, like, Titan doesn't have a magnetic field, but it does have an atmosphere, and it's in Saturn's magnetic field.
Yeah.
So I was wondering if that's ever come up.
Could you rephrase that just a little bit? Like how are
It-
you talking about the charged particles? Oh, sorry, go ahead.
Yeah, like the influence of the if the influence of the magnetic field sort of behaves differently with the charged particles if it's not from like the body itself. So like versus Earth's atmosphere versus like Titan's atmosphere because it's actually Saturn's magnetic field.
So I guess like I'm like I'll give kind of a complicated answer. So from the perspective of like charged particles being like pulled in like raining down onto Saturn and stuff, like not exactly. Like so what Saturn's atmosphere cares about is like is it being bombarded by stuff coming from above is like basically the thing. That stated, like there's probably really interesting geometry that comes about from that and like the like different like ways of like creating just to like zoom back like a little bit. So like with Earth, like we just talk about charged particles that like bounce around magnetic field lines like this. But you probably get like really interesting effects by having like another body that's there that's like affecting those sorts of things. And like a lot of people talk about like how there isn't like a strong magnetic field, but I wouldn't be surprised if there's like crustal variations. We have that with Mars, where like yeah, technically it doesn't have a magnetic field because it's technically dead. But yeah, like you still have like cool effects because there's some sort of magnetic field that's existing here. And I wouldn't be surprised if like there is some small magnetic field that like kind of messes things up and moves it around. So it kind of becomes like a question of geometry and like where things have moved around a magnetic field line. So yeah, I'm sorry that's not like the best answer, but I hope that kind of like adds a little bit. Yeah, okay. Well, thank you.
All right. So our next question is the interstellar medium the vacuum or isn't the interstellar medium the vacuum of space or is it something else?
Sort of. Like we think of it as like a very low density space. Essentially, like there is plasma that will exist there. And before people started talking about dark matter and fun stuff like that, they talked about this idea of like the plasma universe, where technically there's like plasma everywhere. So like it's I would say that the vacuum of the universe like will probably still have like a low density plasma in there. It's just so thin that like yeah, it's not breathable and stuff. Also plasma, you don't really breathe plasma, but like it's not something that we can survive in. It's effectively a vacuum. But yeah, thank you.
I saw. Okay.
When you were talking about your research and specifically when talking about there being more photo excitation patterns in the day versus the night, but that
Yeah.
the night patterns are still present, and we didn't exactly know what that was. Are there any sort of hypotheses or explanations for that, or anything like it working at the moment?
So I guess like first of all, like that's like a one-off example, but like yeah, more generally like we do see that stuff happen. Kind of like my theory, and it's probably correct, but it's just really hard to prove. And I know that's like a great way to like start a science thing, because I have a theory, but I can't prove it. Is that it takes like a long time for magnetic field lines to move around in the atmosphere. So like seeing like those structures existing on the night side, it could be something that has like had plasma moving from the day side to the night side and has moved around and it's just been sitting there for a long time. Like additionally, what we'll have is like just because like this is a very complicated, going back to like even like these plots versus like these plots, we want to like think of like this geometry as being like simple, but sometimes we'll get like more complicated plots that look like this, where we have like reconnection that's happening like in multiple places. And that will completely change this convection pattern. So you can have situations, all that is to say is like you can have situations where you have plasma that's like drifting and it starts to drift back, but then, oh, wait a minute, like something happened on the magnetosphere. Oh no, now I'm back over here. Oh no, like here. And so you can have like weird kind of drift patterns. This is like very idealized. Does that make sense? Yeah. I have a question for you. Is that like a toothless hat? Yes. Okay, cool. Sweet, very cool.
All right. So our next online thing is you weren't well actually'd for the thing you thought you were going to be.
Okay. Oh no.
Because when you said the thing, my first thought, well, technically the Earth is in fact a smaller star. But you were actually corrected on did she and I'm going to pronounce it wrong because I know it will actually annoy him.
Yes. Yes.
A fun thing when our observers join us in chat, I know who you are, and I will purposely just
Troll
dig a
you.
little. He said, "Did she say GIF? It's pronounced or no? Did she say GIF? It's pronounced GIF
I said
with
GIF.
2 Fs."
Wait, is the problem that not that I said GIF, but it's that I'm like GIF? Is it that I said it to them?
No,
Yeah.
he spelled it GIFF.
Ah. GIF. Needs more F's. I say GIF, and that is a hill I will die on. Yeah, yeah, as I should. Thank you, audience.
At
Take
the
that.
point we're arguing about pronunciation,
Yeah.
you know what she's talking about. It don't matter. As long as you know what we're talking about, we're good. When you start going on about like something else and you're like, I have no clue what that is, until someone correctly tells you, you mean rendezvous? Yo, I don't know. How do you spell it? Because you'll have been pronouncing rendezvous as rendivinous your entire life.
Can I have a quick story? So one of my friends was trying to recommend a book for me, and he was like, "Oh yeah, it's this old book by it's about what did he call it? Don Quixote. Yeah, it's like this thing where this guy like chases after a windmill, and I'm like, whoa, Don Quixote? Like, is that what you mean?" And he was like, "No, it's Don Quixote. No, it's not Don Quixote. Like, I don't know." Anyways.
All right. So recovering from that tangent, I think I saw one more question out there in the Rutgers crowd, because we do actually have visiting students from Rutgers.
Woo!
So they have all the good, interesting questions.
Yeah.
Okay.
I was just a little bit curious about what kind of research you're working on now, if you're working on any particular projects that you'd like to talk about, or anything that's happening at NJIT, or whatever you're doing right now.
Okay, so I am still working on this project a little bit. There is a slew of projects that like are kind of complicated to describe. Just because it's like, oh, we're looking at radar spectra, and at first people are like, what are you talking about radar spectra? Anyways, so I'm doing a lot of radar spectra. I also look at, I mentioned it briefly, but this idea of temperature anisotropy, that depending on like the direction that you like look at a plasma, you'll see different temperatures. Because this is the Rutgers crowd, I'm gonna like challenge you a little bit to like kind of think about, like, have you taken like thermodynamics? Basic thermodynamics? Okay, so this idea in thermodynamics that the idea of temperature is really the description of like the velocity distribution. How much particles are going in a certain direction. Cool. So what we find in the atmosphere is that the width of the velocity distribution will change depending on the magnetic field that we have and looking at it. And so there we get the idea of temperature anisotropy, that like if I'm looking at a plasma this way versus if I'm looking at a plasma this way, it'll have different properties. The problem is that we don't have a good validated, quantified like measure of how much temperature anisotropy we see in different directions. And there's a bunch of reasons why. namely because it's hard to measure this effect, but looking at stuff like that. I also look at a lot of ion neutral frictional heating is what we call it, when we have lots of ions colliding into neutrals, and that will cause like a heating effect. And I'm actually using data that's like associated here. So I talked about that, there's a shed over there that was dedicated to a Fabry pro interferometer that's good at looking
I
at.
think that was actually in the trailer on the pad.
Oh, you're right. Yeah, okay, there's a pad over there where there used to be a thing. That's a great story. But it was measuring the neutral winds that were above New Jersey. And then we have these other radar instruments called SuperDARN, or the Super Dual Rural Radar Network, that can measure plasma. So, but yeah, I know it's a silly name. I don't know. But like if we can measure the plasma and we can measure neutrals and we can see how they're flowing against each other and we can measure the temperature in that area, we can see how much frictional heating we have as things collide into each other. But yeah, I can talk more later about like I'm really deep into looking at radar spectra, and basically we get the signal back from the sky when we send a radar signal out. And it's like really understanding what is that signal that we get back. Sure, like we can see that there is a plasma there, and like it's not too hard like really to like see like how fast a plasma is moving or how dense a plasma is, but like you can see really cool effects like Landau damping like in like your in your like radar spectra that you get back, and then you can define all these other cool parameters like the gyro line, the plasma line, the ion line, things like that, and like it gets really complicated from there. But yeah, so that's some other stuff that I do. But yeah, no problem. Yeah.
All right, because I have like 3-4 questions left in online chat. Online chat, if you have any more questions, do start rolling those in, because I actually want to get them answered for you. I don't want to like end stream and you're like, but wait, my question. All right, so our next online question is, we don't use CRTs too much anymore. Who is still actually using CRTs anymore? And why?
I guess gamers. Yeah, gamers still use them because like it's I think it has to do with like you can react faster, like the frame rate's like better with like CRTs. And so to repeat that for online, they composite the images better so the pixels, what did you say?
Are smoother.
Are smoother. So the pixels. It looks better. Cool.
There's a reason why 8-bit you're not insane. 8-bit characters did used to look more round and nice when we were growing up. They didn't used to look like pixel art because of how CRTs did their thing, apparently.
I want to mimic someone in the audience for the camera. Woo! Yeah.
Right. So our next online question, which I think will be a fun one for you, especially after that move. Is the solar wind like a wacky waving inflatable arm man?
Oh, that's cool. Oh, I love that idea. I wish I had some better images of it. I wish. Like it's a little bit more complicated than that, because like you'll have like sections of like the sun that has like magnetic fields that are connecting back, and then those will blast off into space and stuff like that. But yeah, you can have like these interesting like keeping with the wacky waving inflatable arm flailing tube man. Like you can have like these interesting like flares and stuff that like shoot off into space, and like the plasma that like shoots off of the sun will carry those magnetic field lines around. So in that scope, yeah, let's go with it. Let's say that the sun is like a wacky waving inflatable arm flailing tube man.
I mean, you can always come back and do another presentation
true.
with updated graphics.
The title will be Wacky Waving Inflatable Arm Flailing Two Men, aka the sun.
I mean, if you wanted to do a more technical talk too, we do also have our online winter program, which a lot of times we do slightly more technical.
Okay, cool.
Just because not everyone wants to sit outside in the winter in like 15 degrees talking about science, but they will do it from the comfort of their own couch. Was there another question out here? All right, so our next online question. Can you put plasma in a cup and drink it like hot chocolate?
It probably wouldn't taste like hot chocolate.
And the real question is, if you can, should you? Like we have a whole Jurassic Park series going. You were so preoccupied with could you that you didn't stop and think should you?
I think the quickest way I'm gonna answer that problem, or that question, is this plot here. So a lot of the plasmas that I deal with are low density plasmas. So basically, if you put it in a cup in a place where you could drink it, it would probably just drift off into space. That stated, I could just quickly go on a tangent that like you can confine a plasma. So we have these interesting things called like tokamaks and stellarometers, where basically you can find a magnetic field. You can find a plasma through a magnetic field. So that's I'll say that's my answer. If you want to have a plasma and you want to keep it in a certain place, you usually have to use some combination of like electric field and magnetic field to keep it confined there. If you put it in a cup, it might just like disappear out.
So you need a thing with a secure lid and a straw is what I'm hearing.
Yeah.
I don't know. I still am not sure whether we should be drinking
That's true.
plasma.
I mean, I've never tried, and like the scientist in me, I gotta try it now.
So next week I'm going to see a headline. A researcher who just gave a presentation blew up NJIT by trying to drink plasma. I could just see it now. All right, so our next online question, and I think this has to do with the chart where it was like the blues and the greens and
Blues and
whatnot.
the greens. La, la, la.
With the squares.
The
the
blues
pix-
with the greens with the squares. This one?
No.
No.
It looked like a pixel art banner. That
Oh,
one.
That one. This one.
So the one in the center probably.
Yeah. Okay.
Or the slide before that. What do the white squares represent? Was it just like a lack of data?
Oh, that's a good point. Yes, it is just a lack of data, or if it's like too noisy. So there's some filtering that I do here. So first off, there's no data, so I'm gonna just label it with a little white square. But sometimes like we get a huge error back in our data, and like I'm not gonna plot that. So that's a good question. Yes, the white squares in there are just an absence of data.
All right. I just want to make sure I didn't accidentally leave someone's question out. Oh, because I put a reminder for myself in chat. Because you had made a comment about someone not liking SpaceX in the audience. It
Say
was.
that.
I didn't say not. How about let's rephrase it? Not that they didn't like it, but that their reaction was just not overly favorable.
Yeah.
The reaction was not nominal. Although I personally don't voice my opinions on various things just because I think all space and science is neat, for the sake of it being space and science. Honestly, if we could get someone from SpaceX in chat who would actually comment on that, I would chalk that up as a win in my book. I have made it. I have actual like bigwig science people in chat. That would make my day, to be honest.
I would like to actually come back to that in terms of like SpaceX and stuff like that. So like and how it affects my research. So like there's interesting things that SpaceX are doing, and I think that like we're going in a cool direction of like putting infrastructure in space, and that is the natural next objective that we have. And I like absolutely applaud SpaceX for that. I guess where I come in like a little bit more is like worrying. Okay, so like one of the like ways that we can have like blackouts in data is like SpaceX communication that's like swamping our radars essentially. We're moving into this new era, but we have to, I guess, be really thoughtful about like how like the science and the future that SpaceX is moving towards, and like the ethics all combined together. Like it's a shared environment that we all need to use. Like, yes, we should be filling it with infrastructure. That's awesome. But we should be doing that together and like with a lot of thought as well. And of course, like here I could also talk about like space debris and stuff like that. And like luckily the event that happened in February of 2022, like those spacecraft mostly came down. But like as like just anyone, not even SpaceX, like is putting stuff up there, we have to be mindful of that. So long story short, like, yes, we brought up like SpaceX and like space debris, and like they're now adding a lot of like radio frequencies and like signals up there that make it harder to do science these days. And like, it's not that like I'm like, boo SpaceX, boo infrastructure, but just that we need to like work kind of more together to like understand what are the needs of the future. And we need to do it together. I don't know. That's my personal thoughts.
All right. So it, th- that takes care of all the online questions. Just a quick last check. Any more questions out here?
Yeah. You.
All right. So I want to thank you all for coming out. Do have fun viewing through all the scopes for all our online viewers. Thank you for joining us once again. Check us out on our website, our social medias. We love seeing people repeat come out or even just join us in stream. We do this. We are a nonprofit. We do offer these programs for free. So we never expect anything, but anytime anyone donates or even just hits those like and subscribe buttons, we are intensely grateful because it lets us know we are doing a good job and that people want to see more of this content. And with that, everyone, have a good night, clear skies, and good seeing.
Woo.